Hello students, in the previous lecture we have discussed the image position and lateral magnification by refracting surface. Okay, and there we have calculated lateral magnification, which is represented by m, and it is the ratio of height of the image point to the height of the object point with respect to principal axis or axis of the optical system, and the final result was y2 by y1. This is v. V is the distance of the image in the image space from the pole of the reflecting surface, and u is the object distance in the object space with respect to pole of the reflecting surface, and inverse of refractive index of the image space with respect to object space, you can say. And we used, while calculating this magnification, the power. This is the power of refracting surface, which is given by mu2 minus mu1 divided by r, where r is the radius of curvature of the spherical refracting surface. Okay, so now we have discussed the lateral magnification and image position in case of single refracting surface. Now we are to discuss what will happen if we have more than one surfaces. Okay, generally when we deal with optical system, we have more than one refracting surface, or you can say combination of refracting surface. So when we discuss the image position and lateral magnification produced by an optical system, then we will discuss, we will find out this thing due to a combination of refracting surfaces. Okay, so basically optical system is combination of refracting surfaces and the operation. Now we are to connect. Suppose let me make a diagram, and this is the first refracting surface of the optical system, and this one is the last refracting surface. So in between this space there will be propagation of light, or you can say there will be translation and refraction. Okay, there will be translation and refraction in between these two surfaces. Okay, let me write, this is S1, first refracting surface, and this is last refracting surface of the optical system, and this is the optic axis, this is the optical axis. Okay, and suppose a ray moves from this point, this is O, this point is O dash, and it is given by optical coordinates, that is lambda 1 and y1. The ray propagate from this point, it falls on the refracting surface. Okay, and let here this point is P, and the optical coordinates are lambda dash and y dash. Okay, and then after point P, the ray of light enter in this combination of refracting surfaces, that is optical system, and let it emerge out from this point. This is surface S2 and this is S1. So let the ray emerge out at this point Q, and here the optical coordinates are lambda double dash and y double dash. Okay, and after that it propagate, it transfers in this medium, and here at this point let this is I dash, whose optical coordinates are lambda 2 and y2, image is formed. Okay, so here what you can see that O dash is at a height of y1 from the optical axis, and this point on the optical axis, this is O. Okay, so this is the object distance, and let this object distance is denoted by d1. Okay, and the corresponding point of I dash on the optical axis here, that is, let this is I, Okay, so distance of the image position in the image space, that is d2. I am taking it d2. Okay, so now we are to find, now you can see in between point P and Q, or you can say in between 2 points, 2 surfaces S1 and S2, a combination of refracting surfaces is there. So this operation, this combination of translation and refractions is represented by a system matrix. Okay, so simply you can say system matrix is a matrix which connect the optical coordinates of the image in the image space with the optical coordinates of a object in the object space, simply. Okay, so here if we write this, now we need to keep in mind that if you write translation matrix is a 2 cross 2 matrix which is given by 1 0 0. This is the distance of translation and then the refractive index of that medium, and refraction matrix, that is also a 2 cross 2 matrix which is given by 1 minus p, power of the refracting surface, okay, and then 0 and then 1. So both are 2 cross 2 matrix. Okay class, so I have made a mistake, this is 1 here. Okay, now you see, if you find the determinant of translation and refraction matrix, then you will see the determinant of translation is equal to determinant of refraction matrix, and this comes out to be 1. Okay, and the system matrix is combination of system matrix will be combination of translation matrix and refraction matrix. Okay, so if we write the system matrix like minus A, then B and C minus D, so A, B, C, D, minus A, B, C and minus D, these are the elements of a system matrix. Why we are taking it a 2 cross 2 matrix? Because this matrix is made up of product of translation and refraction matrix. As translation and refraction matrix are 2 cross 2 matrix, so their product will also be a 2 cross 2 matrix. One more thing, if you suppose we have a matrix C which is product of A and B, so the determinant of matrix C will be equal to product of determinant of matrix A and matrix B. So in this case, as system matrix is product of translation and refraction matrix whose determinants are 1 and 1, so the determinant of this system matrix, which will be equal to B C minus A D, this will be equal to 1. Okay, so this is what about optical system and system matrix, and using this we will find out the image position and the lateral magnification produced by this optical system in the next video. Thanks for watching.